Hey guys, so today we're going to be going over number 60 in the Physics C-book from chapter 2. So, a rock is dropped from rest into a well. We got a rock, we got our well, and it's going to go straight down. This is going to be also one-dimensional motion. Now in part A, we hear that the sound of the splash is heard 2.4 seconds after the rock is released from rest. So, let's draw this out. We have our ball, and then we have the well in which it's dropped in. Then we have where the ball will be when it hits the water, and this distance let us call x. Now as you know, the total amount of time that the ball takes to hit the water and then for you to hear the sound is not just the time it takes for the ball to fall. It includes also the time it takes for the sound to reach from the bottom of the well and get back up to our ears. So then we have this equation that we can create. First off, let's say that the distance that the rock moves is x. Then the time for the rock to hit the water is t1, and the time for the sound to come back is t2. Now we know that velocity is also equal to distance over time, or in this case if we switch it around, the time is equal to distance divided by velocity. We can say now with this information that the time t1 is equal to the total time 2.4 seconds minus the time it takes for sound to come back, which is the distance x divided by the velocity of sound, which has been highlighted in the problem to be 336 meters per second. Now that we have this equation all sorted out, we can move on to finding the actual distance the rock falls. We will do this by turning to our good old kinematic equation. The change in distance x is equal to the initial velocity times time it takes to fall or move plus 1/2 times the acceleration times the time squared. Now we can start substituting into our equation by first equating the delta x as our distance that we want to find. So x being equal to, now the initial velocity is 0 because the problem says the rock is dropped from rest. So that whole term becomes cancelled. Then we move on to moving down the 1/2 times the acceleration, which in our case is just gravity. And in this case, because we're talking about the distance being positive, gravity itself will be not negative 9.8 meters per second squared, but it will be positive 9.8 meters per second squared to simplify our mathematics. Then we will also move and substitute our equation that we already found above for t1 into the time for t squared, because that is the time that the rock will take to fall. Now for one final substitution, so we can start doing our arithmetic, we will substitute in gravity and then we can finish the problem. As you can see, now after some simple simplification, we get that the distance the ball falls in the well before it hits the water is 26.41 meters. And that is the answer to A. Now, on to part B. In part B, we're asked, what if the travel time for the sound is ignored? So now, we approximate that 2.4 seconds is the total time that it takes for just the rock to fall, and we hear it instantly when it splashes the water. Next, we can again define our distance the rock falls as x meters, and we can now move on to our very trustworthy kinematic equation. Delta x is equal to initial velocity times time plus 1/2 acceleration multiplied by square of time. We can now start substituting into our equation, starting with x being the distance that the rock travels. Then the initial velocity is once again 0, so that whole term cancels out, and we move on to our second term, 1/2 times the acceleration, which is gravity, which is again positive 9.8 meters per second squared, times time, which is now 2.4 seconds squared. Once you simplify this arithmetic, you get the answer of the distance that the rock falls as 28.22 meters. And to actually find, finally, what part B is asking for, we need to find the percentage error, which is defined by this formula as 100% times the approximate value minus the exact value all over the exact value with absolute value signs around them. The approximate value is the distance we just found and discovered in problem B. The exact value is the distance we actually calculated, including the speed of sound, in part A. So now we substitute in for this, so we get 100% times 8.22 meters minus 26.41 meters all over 26.41 meters, and then we get that the percent error between the two calculations is 6.85%. That concludes our math and physics calculations and work for problem number 60. Thank you for watching.